refer to turbulence modeling. If we're going to diverge from the subject, perhaps I will tell someone that will catch up in a different private Zoom, short Zoom, for because we don't want to take too much detours. If the question is too exhaustive to answer, then a few guidance would be, a few words would be said, and then again, we can continue privately because we don't want to lose attention from others. I guess no one wants anybody else to see their faces. That's okay by me. But can you see me?
Yeah, we can see you.
Yeah. Okay. So everything's okay. So first of all, I wanted to introduce myself. I've been doing CFD for about 15 years. Some of you saw my podcast. I started doing CFD my second year of undergraduate studies. My father's old friend was a professor of the CFD lab, and he let me move my numbers from Fluent to Excel, and I excelled at it, and been doing CFD ever since. Used to work at Israel Aerospace Industries, mostly FSI, then running the analysis division in Elbit for about 7 years. Since then, I've been, some of you probably know me from Tenzo, the ANSYS channel partner. As it happens, I'm doing Fluent most of the time, but I also quite acquainted with open source, CCM, and other codes which are, less top-notch maybe. I see there are many new ones joining. So it's a short list. Let's start with Omkar. You want to introduce yourself?
Yeah. Hello, everyone. I am Omkar. I'm from India, and I'm working with Saffron India for turbo machinery analysis.
Mm-hmm.
And so it's been at least 4 to 4 years in total in my career about CFD.
Mm-hmm. Interest in CFD? What's your main focus?
Yeah, main focus on CFD is simulation of mainly turbo machine components.
Oh, turbo machinery?
Yeah.
Okay. So that's low Reynolds, actually, mostly. We're gonna have some stuff to say about that. That's a good thing that you said. Sahin, do you want to say anything else, Omkar? Do you have a special question which interests you? We're gonna go over the questions anyway. We don't wait fun by time.
Yeah. So there is no specific question from me, but as we go along the course, it will be nice to understand all the basic mathematics behind the different turbulence models.
The basic mathematics. So we're not going to do a derivation here. It's not an academic course. It's like the blog. It's communicative. But we are gonna, I've sent you the PDFs. We're going to use them a little bit. If there's something that you want to ask about, I don't know. Why is the realizable model realizable? What good does it do? What's the history of the K omega SST? Why isn't it just K omega? And what's the difference between K omega and K epsilon? And what's wall functions or stuff like that? Sure, you can do that. So Omkar, for you, I have one issue I would raise, and that's the working with low Reynolds.
Okay.
It has close, some issues because you're working in the sometimes in the transition regime, and in your those of you who are acquainted with the law of the wall, your logarithmic part of the law of the wall is very short, it ends quickly, so you need to be very accurate. But we're going to talk about it. Sakhin, you want to introduce yourself? Sakhin Zanjay.
Sorry, yeah, this is Sachin from India, and I'm a PhD student in IIT Bombay, and I've done masters in the CFD course only, and then I've switched over for a PhD. So basically, I work in the field of like external flows and internal flows, which are mainly high speed flows. So for that
Mainly
purpose,
high
like
speed flows.
I would be, yeah.
You mean
Yeah. So
you mean high speed, real high speed flows, like rockets and
not
stuff?
like a compressible flows, but like incompressible means mainly water.
Compressible.
Mainly the water.
So you're doing stuff like boundary layer shock interactions or stuff like that, or
no. Mainly all the things will be related to like incompressibility, such as cavitating flow, that kind of applications.
Okay, so what marks are you working with?
So in my case, it will be fluid is a water or like petrochemical fluid. So Mach number will not be like much higher.
Okay, that's cool. You have anything you want to add? You have a specific question you want to ask? We're gonna go through it anyway. We only have
Not
5
at
minutes.
this instant, but I would go along at the end at the last. So I will ask some question at the end.
Very good. Very good. Sakhin, the other Sakhin. There are two of them. Is that you?
Sorry?
Are you connected twice? Because there are two guys with the same name.
Yeah, my surname is Sanjay.
Yeah, so Sakhin, the other one. Well, never mind him. We'll jump to Oriel. Oriel,
Hi.
like a true Israeli, you allow the video on.
Yeah, I'm sorry, I'm from the PC, so I don't have any camera for now, but maybe I'll
I
connect
can
later
see
on.
that. So so you don't have the balls to show yourself.
And no, but I can put a picture or a wallpaper or whatever.
of Brad Pitt.
Yeah.
So where are you from? Besides Israel?
Besides, like professionally or?
Professionally, yeah, you're an academic, you're
an engineer. I work in the 3D printing
industry. We're at Lambda.
No, Lambda is not 3D. Is they do like regular printers, large format. I work at a place called Massivit. They do large format 3D printers.
Yeah, that's cool stuff. I mean, that's cool stuff. It's cool stuff.
Hello.
Yeah, so so that's like my field for now, and I like this kind of topics because.
So what in particular in turbulence modeling interests you?
For now, out of a hobby, because of a personal hobby, I could relate to that because I wanted to invest more time and
most of the flows are turbulent. Just study?
Where did I study?
Yeah.
I studied in Ariel.
In Ariel. Oh, cool. Yeah. So Ariel is like Edith Avraham.
Yes, Edith Avraham. Edith
Avraham is from Ariel. Yeah.
Yeah. She was my lecturer of fluid dynamics and advanced fluid dynamics and
So I did a few theses for students.
Hello. Hello.
Now, George, you're muted. Do you want to say something? Do you want to skip?
Hi, my name is George. I'm from India. I'm working as an assistant professor in a private engineering college. I've been working with CFD for the past 7 years. I'm also working as a part-time CFD consultant, especially for building aerodynamics. So
let's not talk together. Everybody is going to get this chance to introduce himself.
So that's all about me. I don't have any specific question now. If any question comes, I will ask in the later stage. Thank you, Tomo.
Okay, very cool. Ido, you want to unmute yourself? Ido Binasef. Yes, he doesn't want to unmute himself.
Hello,
Jack, do you want to say? Yeah.
Am I audible?
Yes, Ido.
Okay, so myself Sachin, without the surname.
Sachin, yes. Where are you from? India too?
Yeah, I am from India too.
How long have you been doing CFD?
So basically, I'm doing my undergrad in a private engineering college. So my research interest is related to rarefied gas flows. So yeah.
Okay, cool. Let's see who we have here also. Everybody unmuted except me. Yaniv, can you hear me?
Hello there. Can you see me and hear me?
Yeah. It's Israeli with balls. I can't see you because I see the list, but maybe later I will close the list and then I could see you, but I know how you look. So
okay, sorry about that. As a precaution for safety, I usually block my camera. So if it's a little bit blurred, I'm sorry in advance.
You can block it. There's no reason why.
Okay, sorry, I'm not.
Sorry, I won't block mine. I mean, I won't block mine because I mean, you need to see me talk, but you can block your camera.
Okay. Roger that.
How you doing, pal?
I'm fine, thank you. How are you? Finally, I get the chance to sit in one of these wonderful webinars. I feel really.
Yeah, well, it's the first time of its kind. I mean, it's supposed to be a Q&A, so you must ask questions and I must answer. Otherwise, I'm just going to blabber everything I know about Turbulence and take all the time. But I hope you'll enjoy the webinar. It's not really a webinar, it's a Q&A. So, Yaniv, you're now in Israel or are you still in Italy?
I am in Israel ever since November. I've been working in Italy and studied as well in Italy. I'm an automotive engineer. I've been working in the automotive sector for the past 5 years. I started working in this sector as a student, as an apprentice of aerospaziale in Italiano. It means מהנדס מטוסים in עברית. Aerospace dynamic specialist was my mentor throughout all the university period.
And you should know that Yaniv did some cool stuff.
Thank you very much.
He showed me yesterday. So he's a very talented guy.
Thank you very much.
How old are you?
I've just turned 31 a month and a half ago.
So he's also a baby. So you've got all your future in front of you.
Thank you for the compliment. Thank you very much for the compliment. As an automotive engineer, the thing that drew me into this world of automotive, or especially aerodynamics and flow dynamics, like I like to call it, is because ever since I was a young kid, I used to build model kits of planes and I used to play simulators, and I used to study the entire relationship between nature and bodies and geometries. And in my field of experience in the sector, I've been designing many different aerodynamic extras for cars, parts from chassis to dynamics of vehicles, and even turbulence modeling for internal combustion engines.
Yeah, that's cool. That's cool.
It's a big honor for me to get all these kind words from you, and I feel very flattened, actually.
Yeah, we've been in contact for quite a while, so.
Thank you very much for that. Yeah, thank you. So yeah, I've been working in this sector because it's my passion, and one of my passions in this sector actually is the CAD, the computer-aided design. I've been mastering throughout these 5 years of experience in any kind of workbench or any kind of manufacturing process that is there in the automotive field, which is very much like the aerospace, not really like the aerospace, but very similar.
Yeah. It's just not doing too well in Israel.
I tried going to. I tried to apply to a university in England called Cranfield, but I wasn't. I wasn't ready yet for this type of studies. And later on, I applied for automotive engineering, and I passed all the admission tests. And ever since then, I am in the automotive sector, and I'm pleased for all the rights I've been given to work in this sector, especially in a place like Modena, where it's basically the entire motor valley of Italy, where all the brands, the most luxurious and the most rated brands come from, like Ferrari, Lamborghini, Pagani, some parts of Ducatis. So I've been playing around in the world of this sector for quite a bit. If there are any questions, I'm always here. If anybody needs any kind of help, I'm always here to help.
Yeah, you can keep in touch. Everybody are here from LinkedIn anyway. If they want to introduce yourself.
Hi, can you hear me?
Yeah. You're unmuted.
Well, first of all, thank you for doing this Q&A. I am a graduate student doing my master's in Carleton University in Ottawa. And I still don't have a specific thesis project, but it's going to be CFD related. So okay. I'm just interested.
You mean instead of experimental, you're going to try to do some kind of DNS or larger simulation?
Might be both. Like it might have a part.
That's cool. That's actually what I did.
Well, what drew me to CFD is like I love fluid mechanics in general, and when I got to grad school, I noticed that especially for the aerospace industry, because that's what university is kind of good at, it's always optimization and CFD. So I wanted to learn that. I took a class. I already have the fundamentals of fluid dynamics. I had to take a class for CFD to understand the numerical methods. I did some reading on my own.
Of course, like the Lorena Barber class.
Yeah, and that's pretty much it.
Mostly numerical schemes and stuff like that.
Yes, exactly.
Yeah, cool. So do you have a specific question you want to ask, or?
Well, not a specific question, but I'm interested in knowing more about model order reduction in general.
Oh, reduced order.
Yeah.
Okay, cool.
Because I saw your interview on the podcast, and it's one of the things I read about, and I know it's going to be huge in the future, especially because of AI, which can be linked to it in a lot of ways.
Yeah, it's going to be huge because of a few stuff. We're going to talk about it. Cool. So it's not really related to turbulence modeling, but we're going to talk about it because I think it should be part of the engineering process in any project. And it's going to be so pretty cool that you read it up. Ido, do you want to say something, or did you talk? I don't know. I don't remember. No, I guess not. Omkar, do you want to say something? Rajat. Yeah. Mm-hmm. Okay, if I missed someone, please forgive me. I guess we're going to start. So all of you, I hope, have this PDF in front of you. Are you looking at the PDF, or does some of you? Yeah, you can see my PDF. Okay, so that's a PDF that I gathered from most of my post blogs, most of the courses I led in Tenzo. Each one of them has a link to a post, which is one of the posts in the blog. You can see the 10x and Lumley definition of turbulence. What you can realize for that is that turbulence is a little bit hard to define. It's the last unanswered question of classic mechanics. There's $1 million prize, not for solving the Navier-Stokes equations, but for proving there's a private solution, or there's a solution at all. Here you see the future of CFD. That's kind of funny. I love this picture right now, much more than you can download it from if you'd like. I mean, you can read it. It's amazing. But it was written in 2015, and you can see the guys who wrote it. Pretty amazing guys. But they were way off. I mean, as you can see, there's nothing about machine learning and AI in here, but there was an understanding that we have a problem of a human in the loop. Did anyone not understand? If someone don't understand what I'm saying, just unmute yourself and ask, because it's better for you to understand than to miss a word if you have some problem with English. The human in the loop problem, I mean, the human should check the results, should be the one doing the post-processing. He should not be messing with the mesh too much. He should not be messing with convergence too much. Let's admit another friend in here. So that's what what the vision was about. I have a blog which is pretty pretentious of me to, predictions about the future are quite hard. Or predictions are hard, especially about the future. So everybody of you know the energy cascade concept. Big wars have little wars, and little wars have much more little wars, all the way to viscosity. The famous song. Is there anybody here who can see large scale eddies to dissipating eddies? Is there anyone who can tell me what an eddy is? Who would like to try and say what an eddy is? It's a kind of a mechanism, but you can see what large eddies are, small eddies. Part of the vortex stretching effect. There's also a tilting effect, not just a vortex stretching effect. The vortex stretching effect made made how turbulence is supposed to happen. But there's also a tilting effect, and some of this work was kind of open to the world in the 70s when Andrei Kolmogorov stuff moved a little bit to the west. And amazingly, and we're going to talk about it later, that's when most of the runs modeling started also at the 70s. Until then, they had actually, most of us attribute turbulence to maybe Navier-Stokes, but it's not supposed to be for Navier-Stokes. It's probably for Osborne Reynolds with his famous experiment about Poisson flow and 5,700 or 2,300, but 2,300, right? Reynolds number, of which he saw that in Fitzinger, the seventh has become turbulent flow. But the real true CFD, or if we call it CFD, evangelist of turbulence, in my eyes, was Edward Lorenz with his model to predict the weather. That's because in that time they had computers with an O. That's people doing calculations. And what he saw that the phenomena of chaos, I mean, which really defines best turbulence, Navier-Stokes are deterministic equations, so chaotic equations. This means that extremely tiny variations in initial conditions grow exponentially away from each other, but they have order in this chaos. And there's this beautiful butterfly from Brazil making a hurricane in Florida that we know about. Direct numerical simulations, we can talk about it, but this means we model all the scale. There is no model in the model. In direct numerical simulations, the computer resources rise as Reynolds to the 9.4. If you consider times, it's about Reynolds in third in the power of 3. That's a huge number. And in every publication that addresses DNS, it would say it would not be possible in the foreseeable future. So that's a little bit about DNS, a little bit about the energy cascade, the universal cascade, the integral scale, the interternal subrange, and that's the Kolmogorov scale where the eddies turn into heat, and from there there's a spectral gap between the continuum and the molecular range. If we didn't have this spectral gap, which is mostly represented by the Knudsen number, then we'd have some problems to solve equations. But in turbulence, in the ranges you see here, energy comes from large scales, and then dissipates, goes through the cascade and dissipates on the small scales. Okay, so you have some pump pushing work into the machine, and you have losses on the way by friction, by pressure, and that's how it goes. What you see here is the 5.3. That's the 5.3 Kolmogorov second universality assumptions. Kolmogorov is one of the heroes of mine. He did a lot of work in fluid dynamics. Most of you probably don't know he did a lot of work in computer science too. He has the Kolmogorov complexity, like how you can represent a number with the least amount of data, like a number like pi would need extremely large amount of data to restore. Actually, but you can use the word pi, and then So I guess we're going to talk about Kolmogorov, but it's really not. For those of you who are going to do DNS, I suggest you turn to the. I have a series in my posts about DNS. The most important thing you should know is spectral methods, and if what someone wants to talk about it privately, I would be happy to Zoom about it. So let's go from DNS. You can see here Kolmogorov rules. Very interesting. There's a nice movie here which doesn't work because it's a PDF. But you see here the way we would usually represent, the rotational vector and the strain vector by the velocity gradient matrix. And that's one of the ways also you get the lambda 2 criterion or the Q criterion. So that's the beautiful pictures you usually see when you see, those flying stuff in the air. When there's a high resolution, they say it's a Q criterion or lambda 2 criterion. That's actually somewhat of measure of the amount of defaulticity that you have in a flow and its magnitude. So we can go then. It said resources. That's a little bit old. I guess they have now bigger and better supercomputers. Still, Spalat assumption was that even less would not be possible, feasible as a engineering tool for mass production till the 2070. Okay, now we'll start with the. So, mixing length theory. I think most of you know about. You can't really vote if you know about it or not. The mixing length theory. I have a whole post about it. I'm not going to go into it too much. But what the mixing length theory does, it manifests the Navier-Stokes as emergent equations. Navier-Stokes are able to really predict flow behavior due to the spectral gap that we have between the molecular kinetics and the continuum assumption. We check that by the Knudsen number, and then we can say we can use stuff like velocity and viscosity and temperature and pressure. These are emergent properties. You can say an atom has a temperature or the pressure applied on a molecule, because there's no meaning for such stuff. So that's a little bit. Here's the criterion for the Knudsen number. The input pass should be the mixing length theory is something that relates what is conventional experimental property like viscosity. And it was the beginning of turbulence modeling, the mixing length model, where we assume that a molecule is a fluid parcel. The term sometimes when you're told in aerodynamic videos, air molecules do that, or no, these are fluid parcels. There are no molecules there. The description is wrong if you use the word molecule. And the mean free path is the mixing length. And then he derived a model, which mostly you need to set everything in this model. It's a zero equation model. It works well if you already know the answer for the, or you made an experiment, you know the results, and then you can find these mixing the L mix or the velocity mix, and but it's not used anymore. It's studied, I guess. The Brzezinski hypothesis that stands in the basis of almost everything we do, including the large simulation. The Brzezinski hypothesis relates between the shear stress of the average velocity, between the gradient of the average velocity and turbulent viscosity. And by that, here the Reynolds stress. So there is a connection between the Reynolds stress and the Reynolds stress that you see right here, and the gradient of the average velocity after we do the Reynolds averaging procedure. And what it means in rounds that we model all of the turbulence. So it's a little bit funny because most of the problem is solved by turbulent flow. You have some laminar flow problems like with blood pressure, with blood vessels, and in micro heat pipes or something like that. But then most of the problems we solve are with have turbulence in them, and we model all the turbulence as long as we're talking about two equation models. I'm intentionally not talking about one equation model. I'm going to talk about one equation model, a specific one equation model, which actually is an equivalent to a two equation model. One equation model used to be the derivation for the kinetic energy and differential equation for the kinetic energy, and then some kind of specification of the dissipation of the kinetic energy. It's not used anymore. There's no reason to use it. We have enough computing power. It's not. You'll simply even not find it in code. So I'm not going to talk about it. The K epsilon model. K epsilon model is the most. It's a Q&A. So guys, you must unmute yourself and ask questions every now and then. It's not a turbulence modeling course. We're not going to go through all the stuff if you not ask questions. So anybody has any questions?
Yeah, I have.
Yeah.
At the start of the PDF, you refer to some kind of an eddy vortex or eddy constant. I don't remember exactly what was it referring to, but
eddy viscosity.
Yeah, I wanted to ask about it. I know it probably is a basic question, but I wanted to know what's the meaning of it, and regarding the pictures that you show at the beginning of with the vortex streets,
Yeah. So first of all, the meaning of it is an analogy made by a scientist, which we derived a lot of properties like viscosity and from the kinetic theory of gases. We derive them by doing Taylor series and then cutting it, and then there's a full derivation. You can see I have posted on the Buzynski hypothesis. What he presumed is that we can imagine a molecule to be a fluid parcel. What's a fluid parcel, you ask? It's a fluid parcel. It's above the continuum range, okay? And we can imagine the mean free path. So that's the average path that two rarefied air molecules go before they collide as a mixing length, okay? So he derived the same way you can derive a viscosity, which is a fluid property. He derived an eddy viscosity. The difference between them is that while the viscosity is experimentally verified and it's a fluid property, the eddy viscosity is a flow property, which means every flow has a different value of eddy viscosity everywhere in the flow.
Efficiency.
So
because it's sorry, because we're talking about if we take some kind of aerodynamic wing or body, then if we slice it to different parts or particles, that like every slice will have a different eddy value. Or
exactly, you can say that if it's the plane is at sea level height, then there's 1.2 to 3 kilograms to meters in the third degree of density, and there's a specific viscosity which matches it. It depends on temperature, and it's a fluid property.
No, I know. I'm asking about like the eddy viscosity.
The eddy viscosity is not a fluid property.
Yeah, you told that it's a flow. So I'm trying to ask if we take an aerodynamic like a wing or a plane or whatever, then if it's like per slice, if we slice this profile
then
to
again,
different.
Yes, then you'll probably in flight have a boundary layer, and you'll have a different, and we're going to show it afterwards. It's one of the tips I'm going to tell you on how to check that your mesh in the boundary layer is okay. It's a Florian Menta tip, so you can trust it. And then you're gonna have in the boundary layer itself a huge difference in the eddy viscosity. Outside less, but yes, it's a flow property. It's not a fluid property. That's the big difference, and this difference is huge. So we're basing our Reynolds stresses on the same assumption that you have, for the stress, the wall shear stress equals minus the viscosity times the normal gradient of the velocity, right?
Mm-hmm. Yes.
You agree? Do you agree?
Yes, I agree. Yep. Yeah.
I agree. Okay, so the same. There's a Reynolds stress, but now instead of viscosity there, you have the eddy viscosity, which is a flow-dependent property, and you have the gradient of the average velocity, the one we got from the Reynolds averaging procedure, which I'm not going to show here, but if you want to ask.
Hello.
Yes. Yes, I can hear you. Okay, so yes. Very good. So So we're not going to talk about the shortcomings of the Boussinesq hypothesis. It's enough to say that it has real problem with swirling flows. I mean, it has real problem with curved surfaces because we take the shear stress as what determines the turbulence, and we don't take this. If you saw here, there's a little when I talked about the lambda, you see the velocity. That's the here. We take the stresses, but we don't take the rotational flow. We don't take the part of the rotational flow from the gradient of velocity. So Boussinesq has real problems with the curved flows. It has some more, but since you asked about the K epsilon, we're going to jump right through the one of the arguably most important topics, which is the law of the wall, and jump through to the K epsilon model. Okay. Okay. The K epsilon model was derived in the old school of the Imperial College of London, Launder and Jones, Spalding, all these guys. The first K epsilon model derived what we call the standard K epsilon. It's a high range, so a high Reynolds, which is kind of cool when you're talking about light and stuff like that. But not all flows are high Reynolds flows, and then you kind of get messed up. So you can use it's simpler. I mean, algorithm it's simpler, less arithmetic processes. But the standard K epsilon model, which is, I think it's rarely used. Most of you are told by someone, don't use that, use the realizable model, right? So directly to the K epsilon model. So in the K epsilon model, we have two additional equations. You can see the relation between the eddy viscosity. Here it's the dynamic one, but it doesn't really matter. It's just the rho. You can put it here, and then it's the kinematic eddy viscosity. And there is a relation between the kinetic energy and the dissipation of the kinetic energy. And you solve two more equations of differential equations. One of them for the turbokinetic energy. You solve them together with the Reynolds average Navier-Stokes equation. So Reynolds average Navier-Stokes equations. The issue with the K epsilon standard K epsilon model, no, but most of it here is on the standard K epsilon model, is that it has some problems. It showed that it predicts separation too early than found in experiments when we're talking about, let's say, airfoil or wings. So this means that the flow becomes turbulent a little bit earlier. And it's a high Reynolds model. This means that you can use it only when the Reynolds is about 100,000. And another problem, and the major problem probably, is that we didn't talk about the law of the wall, but the turbulent boundary layer is comprised of 3 layers. One of them is the viscous sublayer, which is Y plus. Everybody knows what Y plus is. If someone wants to say, I don't know what Y plus is. I want to go back and explain what Y plus is. You can say that after I answer this question.
Sorry to interrupt.
So it has
about the Y plus part. Like I've studied it,
yeah.
But is there any physical meaning that you can provide to give more intuition to it? Because for me,
It's a kind of a Reynolds. It's a kind of a wall Reynolds number. Okay, but the velocity in this Reynolds number is based on the friction velocity.
Okay.
Okay. So you can. This part is between Y plus. It has no dimensions,
okay.
And but you can calculate a Y from this Y plus. Even you can see it in the PDF. It's between 1 and 10. There's no smooth connection between them. The connection between them comes through perturbation theory, which we are not going to talk about.
Okay.
Then there's a buffer layer, which connects the logarithmic layer, which is, you must understand when you look at the graph of on the graph of the law of the wall, you must understand that's a logarithmic graph, okay? So 1, 500, 1,000, okay? So that's this part here, this viscous sublayer, sometimes called the laminar sublayer, is somewhat, you want to continue until after 7:30, or you want to do another Zoom sometimes else?
That's completely up to you.
I'm okay with it. We can go to late. We can go to late if you want.
Sorry to interrupt. But in a way, the K epsilon model that you've just showed is one of the fundamentals in every wind tunnel.
Yeah. I'm talking about this because it's going to be directly connected to what I'm going to tell you about the K epsilon model. Okay? Okay, so this one is the viscous sublayer. It's actually linear. It's also called the laminar sublayer. This is a buffer layer. Usually in ANSYS, in Fluent, they have a number which is 11.225, which depends on if it's below that, it's a viscous sublayer. Above that, log layer has something very interesting in it. It starts in white in an ending. It's longer as the Reynolds is larger, which means that if I have a low Reynolds velocity, a low Reynolds like in turbo machinery, then the log layer could end at about 400, and I need to take it in mind to have the fine resolution to capture the log layer. Okay, if it's an airplane, then the log layer can stretch about 5,000. Okay, so there's intentionally no number defining the end of the log layer, and it's very important. After that, it's the defect layer and the free flow. Going back to the K epsilon, what they found out is that the epsilon equation could not be integrated, could not get Dirichlet boundary conditions. Dirichlet boundary conditions, I mean, epsilon equals 0. It could not be integrated to the wall, which means that the model is very problematic. We need something to overcome this. If it's the standard K epsilon, then what we do usually is use wall functions. It means we use the K epsilon above some Y plus equals 30 or 70 even. And then we connect some wall function, which gives us some velocity, which is there. The velocity is not 0. There's no non-slip boundary condition. okay? Because we cannot integrate epsilon equation to the wall. So that's why one of the biggest problems with the K epsilon is that it is wall sensitive, okay? And it doesn't matter which one of the K epsilon you use, it's wall sensitive, okay? Then there is the realizable K epsilon. The realizable K epsilon has no problem with the, it's not a high Reynolds two equation model. And it came, and sometimes, I mean, ANSYS, at least ANSYS, and probably most of you are either using the K epsilon realizable or using the K omega SST. Probably most of you using the K omega SST. The issue with the K epsilon realizable is that there are some constraints on the principal stresses, which means that it performs better when the flow gets stagnated. So it drives the performance of the model a lot better, but you still need to use something to avoid the issue of not being able to integrate the epsilon equation to the wall. So you have two ways to go. One of them is, again, wall functions. You start from, you put your first mesh, I mean, it's actually the middle of the cell. It's y plus above 30, and you use a wall function. The other way around is using a low Reynolds model. And just to be clear, a low Reynolds model is not a transition model. What a low Reynolds model does, it has damping functions, very nonlinear damping functions. If some of you know the word Van Driest, and what it does, it actually damps it switches from the K epsilon to some kind of damping functions to be able to achieve the boundary condition, the non-split boundary condition. So that's about the realizable and standard K epsilon. So never use standard K epsilon if you think you're not in high Reynolds and you're not going to use wall functions. And you can use the realizable K epsilon if sometimes it performs better, because if the flow has lots of stagnation points, then it might have might perform better than the K omega SST. Okay.
Can I ask a question about it?
Yeah.
About your last sentence, that stagnated flow will perform better. Will it perform better only software-wise or aerodynamically-wise? I'm trying to ask if you're referring to energized flow, like forcing stagnation points in order to energize the airflow.
No, I mean, you just want to predict stagnation when the flow hits a wall, so you don't want to get rubbish there.
So it's software wise in order to get like
no, it's also aerodynamic wise. I mean, you could have a place of stagnation. Imagine a flute with many pipes going through it. You know, one flute with pipes along the way and the wall in the end. You have a stagnation point there.
Yeah,
you want a model which can raise the pressure correctly to divide the flow between those pipes. So the realizable model has some advantages in this regards. And you don't need to play with the constants. I mean, there are constants which were derived by experiments. Usually, there's no reason to touch them unless you know what you do. most of the turbulence modeling world was the main contributor to the turbulence world. Two of them were Philip Spalart and in the last 20, 30 years, to the turbulence runs world, I mean, or the hybrid runs less world, were Philip Spalart from Boeing, you know him probably from the Spalart-Almaraz model, and Florian Menta from ANSYS. Did anyone want to talk about the Spalart-Almaraz model? Anyone have any question about it? Again, about the K epsilon model, what do you want to know? Oh, the standard K epsilon is a high Reynolds model. It's a high Reynolds model. You should use it when you have high Reynolds. You should not use it when you don't have high Reynolds. When the flow suffocates, or when you have, then you might have problems. It's a high Reynolds model, and it's very wall sensitive. It's very wall sensitive. What you have is the K omega SST, I mean, or the K omega baseline model, which I'm going to tell you a little bit of the story about the K omega model. The first K omega model was actually devised by Andrei Kolmogorov, but it was never coded. It was never even out until the 70s. All the meaning of omega taken afterwards by David Wilcox, which, if any one of you want his book, you can contact me. It's not in print anymore, so you can get it. I think it's one of the most amazing books ever. So actually, the first K omega, which was coded, was the Wilcox K omega, and it was coded to remedy the problem of the sensitivity of the wall sensitivity of the K epsilon. But what was found that K omega was not wall sensitive. You could integrate it to the wall, no problem. But then it had problems with the omega equation in the free stream. So down came Menta, then he was in Asa Langley in 92, and said, why don't we combine between the two? And we solved the K omega inside a portion of the boundary layer. And then he did what he does a lot. He used switching functions, blending functions. Most of his work is about blending functions. It's transition and blended the K epsilon model with the K omega model near the wall, with the K epsilon model outside of the middle of the boundary layer. And then you get a model which is actually K omega near the wall without wall sensitivity, and K epsilon where there's no omega sensitivity. That's the K omega baseline model, BSL. Then he took another assumption and saw that, and it did show that the model performed a lot better with prediction of separation also. That's the main thing. And the other main thing, it's not wall sensitive, it's wall insensitive. So it doesn't mean that if you want to get results for drag, that you don't need to model the viscous sublayer. You still need Y+1, okay? But it means that you don't use a low Reynolds model for that. Okay, understood? Low Reynolds application might involve transition flow. They might involve the log layer, which I told you when I showed you the law of the wall. The log layer might end at 400 Y plus. So you might even not have a log layer, okay? It's very problematic, especially for turbo machinery flows. Usually in turbo machinery flows, we work in the low Reynolds regime. So we take very good attention, pay very good attention to sometimes using transition models, the LCTM, the transition model of Menta, or using some kind of prediction to high resolution. In high Reynolds flow, you have less problems. I mean, transition is a very obscure phenomenon. It has many mechanisms. It has the natural transition, the one you see on airplanes, the regular Turbulence waves. It has the phenomena which you usually see in turbo machinery, which is bypass transition. You have many kinds of transition mechanisms. It's something which is still investigated. And, so that's the main difference between them. Okay, again, if I'm returning to the K omega SST, so the addition between the baseline model, which already connects between the K epsilon in the innermost portion of the boundary layer and the outermost portion of the boundary layer with omega, is what's called the Bradshaw hypothesis. The Bradshaw hypothesis changes changes the weight of the kinetic energy versus its dissipation. And what it does, it makes the model a little better for flow which carries some non-equilibrium. A major example for non-equilibrium flow could be a jet flow hitting the wall. I mean, that's a non-equilibrium flow, but you can get non-equilibrium flows for many reasons in complex geometries. So that's why everybody always say in closed systems use the K omega SST, because you might get regions with where the flow will become a little bit non-equilibrium. I mean, between the kinetic energy and the dissipation of the kinetic energy. And then the Bradshaw hypothesis, which I think I'm gonna show you. Near wall treatment, you can read about it also. There's a lot of stuff done on that. You have here, I sent you the PDFs. If someone wants, I don't know, I think you can get through the post through the PDF also. There's not supposed to be any problem. So that's the Bradshaw hypothesis. It made a connection between the kinetic energy and the shear stress. And this improved a lot in non-equilibrium flows. And that's actually the model most of you use right now. I think the links work here, so you can, if you press any of the links, you'll get to the post and you can read everything you'd like about let's talk a little bit about the Spalatal Morass model, or anybody else has a question he wants to ask before. It's a Q&A. I'm kind of a regular course guy, so anyone has a question? He needs to unmute himself if he has a question. No questions? So the Spalart-Almaraz model. Spalart-Almaraz model is a one equation model, but it's a one equation model for the eddy viscosity itself. So if we had this eddy viscosity was some alpha times K kinetic energy squared over epsilon, then now we have one equation for the eddy viscosity itself. So it's a one equation model, but it's a one equation model which is should consider be a closed model. We have everything we know. We don't have to guess no length scale or velocity turbulence scale or velocity time scale. The issue with the Spalart-Almaraz model is that it was I'm going to have to do a little change here, so you guys should excuse me. Can you hear me?
Yes, we can.
Yeah, we can hear.
Okay, now it's better. Now, right? Can you hear me now?
Yes.
Yeah, we can hear you.
You can hear me. Not very well, but you can hear me. So the thing is that Spalart, working for Boeing, he derived this model by fine tailoring of the model to work for aerodynamic flows, external flows. He kept improving the model so it could withstand swirling flows. It's a wall insensitive model, which means that you don't have to use any wall functions or anything like that. So if you have a problem with and it's the basis for the detached eddy simulation hybrid model, monolithic hybrid model, which is Spalart's model, the DES, if you know what I mean. I think most of the aerospace industries use this model. They can by all means use the K omega SST, but this one is simply perfectly tailored for aerodynamic flow. So that's kind of cool. The rotation correction, the transition modeling. I did my thesis on transition modeling, a specific kind of transition modeling called the bypass transition. Usually you could find it bypass transition in turbo machinery. Bypass means it bypasses the natural Tolman-Schlichting wave kind of way that we usually find on airplanes. That's little disturbances, which turns to coherent structures, which turns to turbulent spots, and then turbulence. What they did is they used a large amount of data, and that's why it's called LCTM, it's local correlation. And actually the local correlation model, turbulence model, fits quite a few mechanisms of transition, although it's trustworthy when prediction of transition is not of the most importance. I mean, the exact point of transition, or there were other ways to calculate till then transition, the EN method, and combining stuff like the EN method, solving the Sommerfeld equation. It's a very huge and sophisticated and still investigated and very unknown topic, but it seems to work at least by the validations that ANSYS proposes very well. It was devised by Volker from General Electric and Menta from ANSYS, and you can use that if you think you have a transition issue. I mean,
if I remember correctly, sorry for interrupting, this model is used for ducts, mainly for ducts.
It's used also for turbo machinery. It's one of their validation shows an helicopter, but yes, in ducts, especially in when you take blood flow as not as a Newtonian fluid, and you have low Reynolds, then the transition model could improve the results by a huge amount, because most of the flow is laminar, and then you have some areas which turbulence develops because of
the geometry of the duct,
or something like that. Exactly like that. Exactly like that.
Because especially this sorry for interrupting again. This model is used a lot, especially in two-strokes engines. Because of I remember when I simulated a lot of two-strokes for fun, and was like an enthusiast for racing and things with the racing guys of Italy. We used those models in order to design the inlet and outlets and the ports.
It's Yaniv, right?
Yeah.
It's Yaniv talking, right? Yeah. Exactly. We spoke about it yesterday. Yeah, exactly. But again, you should remember that there's no real theoretical basis between the work you see here, which was done by Dan Henningsen and Philip Schlatter and all of them, and the work that Menta did. But here you see the bypass transition, my favorite kind of transition. Yes, you can use that in ducts. I used it. I didn't use it for a car, but I used it for a duct, which is a vein. Apparently, I had a transition regime there, and you could have seen it, because if you took the velocity profile, you could have seen it's not parabolic, but it's either not like a turbulent profile, which is like a square.
Wow, the boundary level must have been a pain in somewhere, if I'm what I mean. With ducts.
Exactly.
Yeah.
Another K epsilon model is the V2F model. The V2F is actually a K epsilon model supplemented by two more equations for V squared and F, which mostly was devised to resolve the problem of swirling flows. My feeling is that the model didn't prove itself too much. It has an elliptic nature. Elliptic nature, when we talk about partial differential equations, is that like something that happens in the domain is immediately communicated to the boundary. So it kind of communicates with the wall. It's the same in the K omega model, actually, but you have some. It's supposed to be a little bit more better for flows with rotation and curvature,
in my opinion, and in other more esteemed individuals, it hasn't proven its worth, and it's actually even in Fluent. It's an option. You need to open it. I even wrote here how you open it in Fluent. So that's another K epsilon model. Beyond this, there's the Reynolds stress models, which you probably never had the chance to use. If some of you did, please raise your hand. The problem with the Reynolds stress model, it doesn't use the Boussinesq hypothesis. So it solves an equation for the Reynolds stresses. It actually solves somewhat like 6 additional equations beyond those you solve anyway, which is 9 equations, and all of them are very, forgot the word, Tsumadot, very, it's supposed to contain more physics, but it actually very hard to converge, and it's not worth the time, as now we can use hybrid models, and which give you more turbulent content. In RSM, in Reynolds stress models, still all the turbulence is modeled. Then we go to the scale adaptive simulation model, which I know all of you used a lot. It was developed in about 2003 by Mentor and Agorov. Agorov and Mentor still work together. I used to see emails between them. And the issue with them is that they took Rhodes' equation from the 50s, who tried to and made some changes which allowed the model to not break to what's usually happening is that 2 little eddies combine to 1 big eddy, and we can't see turbulent content in runs. This doesn't happen with the scale adaptive simulation, but as far as I see it, the scale adaptive simulation model, which is a transient model, of course, gives you the turbulence colors, but give you the turbulence content, but it's mostly colorful for directors. You can derive second order and higher order moments from Fourier content, which makes sense from which you have to do in large eddy simulation, for example. So it's not really useful unless you want to produce really beautiful pictures. It doesn't have big demands you should have if you're using scale adaptive simulation for say I don't know,
vortex generator.
Vortex generator above a pipe, or then 20 cells per diameter would do. But you should consider that it should be not only on one direction, okay? You can't have stretched cells, because then you won't have the turbulent content. That's the same problem with DNS and large eddy simulations. Going for that's ANSYS's recommendations for either use the realizable K epsilon model which shows good performance in closed spaces. I mean, electronic devices where you have turns and stagnation areas. Usually runs model over predict corner flows. Okay. Either they over predict the corner flow. You know what I mean? If you have a square duct,
yep,
you get like corner flows. They over predict the corner flows, or you get total rubbish. I mean,
I call it this, the המפריעים של השכונה. The disturber, the those that makes all the noise and the
yeah. So all these models are very problematic with corner flows. They over predict because of the way the Brzezinski hypothesis is synthesized. They over predict a larger area of the corner flow, or either predict rubbish. So if you have a square duct, don't use this kind of models. You see here in blue the K-omega SST and a little bit about why they think it's better to use it. Large eddy simulations. I guess some of you are going to do. Large eddy simulation are getting a big breakthrough right now because of combustion, especially because of combustion. I'll admit him inside. Especially because of combustion, because most of the action of the flame is away from the walls. The issue with large eddy simulation is that you resolve the large scales, and then you decide upon some kind of resolution which was unresolved, and then you use a model. The funny thing is that you need to define where you put what's the size of the filter. So in the K omega, in the K epsilon, you don't define anything. It's a closed model. Large eddy simulation actually is not a closed model. You have to define a filter length. But you get, because of the universality, and you can see the SGS, which means sub-grid scale model. There you have many models. You have the Smagorinsky, which is rarely used now because it has many problems. It can't perform when the flow becomes laminar. There's the Vale model, which is used a lot, and the dynamic model, which is used a lot. The problem with large eddy simulation right now is that the demands for wall-bounded large eddy simulation is comparable with DNS. I mean, the smallest, the highest resolution, the near resolution would comprise 90% of the cells, and should be of the size of the Kolmogorov's length scale, which is what you have in DNS. So actually, the less, as you see here, ready 2070, that's Pallard's assumption. We would probably be able to perform, if Moore's law keeps, doubling the way it does, and suppose it could, but it's not so obvious. Then in 2070, I don't think I want to live until 2070. I think. Then we're going to have the ability to perform a large eddy simulation to a full airplane. Besides that, you have message of hybrid light SGS modeling. Less has the large eddy simulation have much more demands than Reynolds average Navier-Stokes. I mean, the inflow is very important. You must produce the flow which has the right turbulent content, which usually when you use the runs, you only define a turbulence intensity and some kind of length scale. Here you must have, so you either have to, internet connection is unstable. I don't know why. So you either have to run a large eddy simulation. If it's a pipe, then use a very long pipe, or you must recycle the results. I mean, a few times for the inflow conditions, or you can use vortex generators. I think it's all written here, but each method has its. You can also trip the flow and create turbulent content, but inflow conditions are very important. Outflow and boundaries are also very important, because if it's compressible flow, then and an outflow condition could have a backflow effect and ruin the results. So sometimes you must damp the outflow. Generally, there are many special temporal resolution, validation. Validation is very important in large eddy simulation. Usually when we do Reynolds average Navier-Stokes equation, we're interested in integral quantities like lift, maybe some kind of average velocity and a pressure distribution. In large eddy simulation, we usually want higher statistical moments, to derive higher statistical moments, to actually understand if we got the right turbulent content, which is kind of an issue. So less validation is an issue. Then we go to hybrid methods. There are two kinds of hybrid methods ruling right now. Now, there are actually three kinds, but two kinds. One of them is the monolithic, which is the DES family, which includes the detached eddy simulation, where there is some kind of grid size, which if we're lower than this grid size, then what happens? It turns to less, and when the grid size turns larger, it turns back to runs. Then you can because you have near wall problems, you can solve runs near the wall, and you can solve large eddy simulation away from the wall, and then you don't have this computational effort problem that you usually have with large eddy simulation. That's a monolithic method. It depends on the grid. Then there is the zonal method. Then you actually divide the zones to zones which are large eddy simulation and zones which are Reynolds average Navier-Stokes simulations. And between them, there's a gray area which needs to be connected, because when you move from a Reynolds average Navier-Stokes zone to a large eddy simulation zone, you actually have to have the turbulent content, which you don't get from the Reynolds average Navier-Stokes method. Some remedies are used is to use the scale adaptive simulation as to have the turbulent content going into the large eddy simulations. There are others. That's just short Q&A. It's 8 o'clock. It's getting kind of late. There's a lot in turbulence modeling, isn't it? Hybrid method, detached eddy method. detached eddy simulation. They found some problems with which is called model stress depletion, which means that the flow turns turbulent, turns to runs when it shouldn't, and it turns to less when it shouldn't. So they shielded the boundary layer from these disturbances. Out came the shielded detached eddy simulation, and so it goes on and on and on and on. And the final one that Menta created in 2013 is the stress blended eddy simulation, which is another, it's not really a model, it's more of a modulation, it's more of a modular approach where you can choose the runs that you want, because the original detached eddy simulation was with the Spalat Almaraz. The same Spalat Almaraz you use for the runs, you use for the large eddy simulation. But stress blended eddy simulation allows you to use, let's say your favorite or your validated and well-known large eddy simulation with your favorite runs, and the secret is how the transition between them goes. And it also allows the WM less. If some of you saw the pictures I put in my posts, which is wall modeled large eddy simulation, which means you have a very small portion in the innermost portion of the boundary layer, which is runs, and all of the rest of the simulation is large eddy simulation. And then you can actually do a full airplane simulation. The issue is how you trigger the last mode, the large eddy simulation mode. Any questions by now, or we've talked about embedded zoneless. These are all the models you have. You have them in Star CCM. You also have them in Fluent. You have a post of each on each page here has C link 4, sync link 4, C link 4. You can read the post about it. It connects you directly to the All About CFD blog, and you can use it. Questions? There is an example workshop you can do to calculate Y plus. You can either use that will give you the same answer as the pointwise automatic one. If you type pointwise Y plus, you get a Y plus calculator, or you can use this. I have an Excel if someone wants. It's very easy to do that. It's taken from an ANSYS course. I stole it from them, but this one is mine. It's a little try. Any questions, friends? Something unclear? Everything unclear?
Tough crowd.
You can unmute yourself and ask questions. Feel free to ask whatever you want. I mean, it's a very large topic. It's a topic that in Tel Aviv University was taught for a full semester. I was already into turbulence modeling a lot before I started my thesis. So it was very kind of easy to me. And the one who taught the course was the brother of, he teaches it was a one-time course in Tel Aviv. He teaches in Ben Gurion University. And he's the brother of the one who invented the NRG, the group normalization theory K epsilon model, which we didn't talk about because it's I think it's too much information to
It's gonna make a salad.
No, it's a very rigorous model. What they try to do there is based on vocabulary from quantum field theory, and then the Q&A would become very. But I'm intending to write a post about the energy model soon, which I hope you'd like. Any questions?
Sorry to interrupt, but when we talked about the SST model, I had a project once where I had to compare between SST and the K epsilon for supersonic flows, and the K epsilon actually proved to perform much better than the SST. I was just looking at the slide you have open, and there's nothing about that kind of flow, so I was wondering if you have any intake or recommendation for. So it was a conversion-diversion nozzle.
Yeah. That's an issue we didn't raise. Supersonic flows and even beyond that, there are issues that, first of all, I don't know how far you got with the validation. If you got first order data like lift and drag, or did you do higher order moments, or but the issue with supersonic flow, and even more than that, is that it's a field which is still very much investigated, especially when you have shockwaves and boundary layer interaction, where it's a problem which we haven't still investigated thoroughly. It's still work in progress. So it's like I have to say something that it's to everybody. So many people obviously turn to me and send me emails about. I get like 100 emails a day with questions. Some of them are on multi-phase flows and supersonic flows, high Mach number flows, real high Mach number flows. Those are subjects that are still under research. We still don't know too much about boiling or cavitation,
friction,
or even friction. But turbulent flow, and especially in very high Mach flows, all the chemistry breaks down. And so jumping on questions about I can tell you the difference between DPM and VOF. It's a question of resolution, but really solving a problem like I had a project with someone which was micro heat pipes, which were based on boiling, and it was such an we got our correlations quite okay, but it's a subject that we usually don't really know. It's still under research, so it's very hard to answer your question about why the K omega SST, because actually when you think about it, the K omega SST is K epsilon in the outermost portion of the boundary layer, right?
Exactly. Just to clarify, it was a flow through a CD nozzle, so there was no lift or anything. My validation was done through that I would solve it analytically, predict the shock wave, predict its location, and then run the simulation and see if it matches. They both they predicted different shock wave locations, and the SST failed to predict overexpansion.
Yeah, So it over predicted actually?
No, it didn't. Like the overexpansion case, it showed it as a no shock. It was perfect in SST.
It's a no shock.
Yeah, but for
so
K
the
epsilon,
K epsilon,
there was
the K epsilon. That what I think that it over predicts shocks actually predicted a shock.
Predicted it. Yeah. And I
Yeah.
I knew that was the case because I had already solved the pressure ratio with the area and all of that and done the analytical work.
Yeah, but it's a very good thing that you did. I mean,
it was quite interesting.
Trusting CFD without validation is like, unless you're very greedy or I mean, trusting CFD without validating it is, or unless the resolution is not so important, like in electronic devices and stuff like that.
Yeah, one of my professors calls it colorful fluid dynamics. If you don't validate set of computational
colorful for direct.
Yes, exactly.
Yeah. And you give them in the beginning, you give them the, managers, 2 sentences, did this, did that, everything's good.
They see the pretty pictures, they're sold.
Yeah. They turn all the pages to the pictures, and when I remember when I was in Israeli aerospace industries, and I was in Elbit actually, and we had a project with the Israeli aerospace industries, and I had to make a CFD report, and the guy and we were subcontractors for Israeli aerospace industries, no matter the client, foreign client. And then he comes to me and he said, "What the fuck? You write too much about the turbulence modeling and the way you're gonna make them ask too much questions. That's going to be a huge failure." And I said that no, that's exactly what I want to do.
That's the point of
it. That's the point of all the. I prefer to answer all the questions than talk about the results. But yeah, anyone else? Any questions about specific models?
I don't have any more specific questions, but I would like you to talk about reduced order models if it's possible.
Reduced order models. Okay, so I talk about it a little bit. I'll give you an example of reduced order models which you've probably used for years. That's the analogy between thermal resistance and resistance, as you know it from Ohm's law. The potential difference equals the current times the resistance. The temperature difference equals the heat flow times the thermal resistance. So you can specifically, you can actually represent a network of resistors